So our last set of notes here for chapter 8 in chemistry is all about an activity series. So make sure you print out your notes for this section, or at least open up that PDF so that you can see what the actual activity series is, because I just typed it down the side of those notes. So you have to have that available for you to use it, right? There's more than just the element that I put in the slides here. I just have groups of elements that are represented by one, right, by the head of that group. So make sure you have the actual notes and/or look at those actual notes so you can see what the full activity series is. But we use an activity series to decide from section 2 which single displacement reactions will work and which ones won't. Because just because one metal might replace another doesn't mean it's actually going to happen. So again, that second objective there says use an activity series to predict whether a given reaction will occur and what the products will be. Right? We've already done single displacement. We've already covered that. We just need to understand that although in section 1, even right away, right, in your homework quiz, you had that aluminum that was displacing copper in this cuprous nitrate, right? So I had a solid aluminum, I had an aqueous cuprous nitrate, and my products, aluminum just flip-flopped with copper, but an aluminum nitrate looks a little bit different than a cuprous nitrate, so I have to balance things differently, right? Understanding that, okay, maybe I'm going to need 3 nitrates on both sides, and therefore I'm going to end up with 3 coppers at the end. But this reaction only works because aluminum is more active than copper is, right? Any active metal can replace a less active metal. Right? So when we look at an activity series, aluminum is higher on the list than copper is. Right? But if I change this reaction up just a little bit, if I tried to have, okay, magnesium, maybe it could replace, and let's call it a calcium nitrate instead of copper nitrate. So this will balance a little bit differently too. So can magnesium replace calcium? Right? If you look at the activity series, if you have that printed out list, calcium is in that top group with lithium, and magnesium is in the second group. Magnesium is definitely below calcium, which means that magnesium is less active than calcium, right? So our first thing that we're supposed to learn from this activity series is that, yes, aluminum can replace copper because aluminum is more active than copper. But no, magnesium cannot replace calcium. So if I was given this prompt, I'm actually just supposed to write no reaction. Nothing would happen here. Right? Calcium can replace magnesium, but magnesium cannot replace calcium. You gotta understand the difference. So if aluminum's higher on the list than copper, then you can go ahead and make products. But since magnesium is not higher on the list than calcium, right, this does not work in the second example. So know when these single displacement reactions can happen and when they won't. Only active metals, more active metals, can replace less active metals. But again, I don't have the full activity series in your notes. I only have little representative sections here, right? Lithium's at the top of the group with lithium, rubidium, potassium, barium, strontium, calcium, sodium. I didn't want to put all those in on this slide right here. But anything that lithium can do, the rest of those elements can do, right? And magnesium's the head of the next group, and cobalt's the head of the next group, and hydrogen's at the top of that fourth group. Silver's at the top of the bottom group. So each one of those elements just represents a group. And lithium's group is the most active, it's at the top, and silver's group is the least active, all the way down at the bottom. But for each group, they are grouped the way that they are for a reason. That first group is very, very active. Lithium is, right? Rubidium is, potassium, barium, strontium, calcium, sodium, right? All of those metals can react with water, which is a very stable compound, understand, and displace hydrogen to make metal hydroxides and a hydrogen gas. Right? So we're going to talk about what reactions each one of these groups can do. We're also going to have actual representative examples. So on the next slide, I'm going to do an actual one with lithium, with one of the metals in that group, so you can see what it looks like. But this is just generic right now. If that metal reacts with water, it's going to make a metal hydroxide and hydrogen gas. Right? Now, the important thing to understand here is that's the exact same reaction I'm going to have for my second group. Right? Magnesium's group. Those metals can also react with water, but they don't make metal hydroxides. They make metal oxides. There's the difference. And hydrogen gas. Otherwise, it's a fairly similar reaction, right? But those metals are less active. And actually, because they're less active, the conditions have to change too. So what you're going to be looking for to tell you, right, whether one of these reactions would happen or not, right? Lithium and its group are so active that they can react with cold water, right? It's perfectly fine for this water to be cold, and they're still going to be able to react with it, right? Now, typically, I'm going to indicate that that's cold water in a couple different ways, right? I could say that it's a liquid, right? Because actually, that is relatively cold in terms of temperatures, right? Water is a liquid at room temperature, and that's not hot water, obviously, right? So, cold water, right? I could just say that that water is liquid. I might put any temperature over the arrow. Doesn't matter if it was 2 degrees, 5 degrees, or 1,000,000 degrees, it would work no matter what. Because lithium is really, really active, it can react with any temperature of water to make metal hydroxides and hydrogen gas. Whereas magnesium is less active than lithium. So it can only react with water if water's hot, right? If that water is really hot, which I can indicate in a couple different ways, right? I may say that it's a gas, that it's steam, right? But I know for a fact that it has to be at least 100 degrees Celsius to make that change, right? You could actually have water as a liquid at over 100 degrees Celsius. You just have to have a huge pressure on it to keep it as a liquid. But either way, as long as I reach that 100-degree threshold, this reaction could occur. So magnesium doesn't react with cold water. I can't throw that magnesium ribbon into water and have it react automatically. But if that water is hot, if it's steam, then definitely that reaction will occur. But I also make different products. I make oxides instead of hydroxides. So look for the conditions first and foremost, right? If it's magnesium, the water has to be hot. If it's lithium, water can be cold and it will react either way. Cobalt's group, right? That group also does things a little bit differently. This time I'm not worried about water. In fact, cobalt can't react with water. It doesn't matter how hot that water is. Water is too stable for it to displace hydrogen, right? But since cobalt is technically above hydrogen over here, right, it can displace hydrogen in other compounds, right? But it just can't be water. So maybe I have an acid, right? I meant to make that generic to start, so that is an acid. I'll do that on the next slide. But these metals can react with acids to make salts, a salt of some kind, and hydrogen gas. And again, I'll give you specific examples on the next slide. But as long as it's an acid, as long as it's not just water, right, you can replace hydrogen as long as you're above hydrogen on this list, right? And cobalt is directly above hydrogen on the list, right? Because hydrogen's the next group. It's the top of the next group. And so any of the other metals in that next group obviously could not displace hydrogen because they're below hydrogen. They won't be able to replace hydrogen in an acid. They won't be able to replace hydrogen in water either, right? So each group has something new that it can do, but understand also that the groups above should be able to do anything below. Remember, lithium could react with water, hot or cold, but lithium can also react with an acid to make a salt and water and hydrogen gas. So we'll talk about how this works as a whole as we continue to do examples, but just make sure you have a good representative example for each group. Hydrogen's group, though, again, these ones, if you take any one of those metals, and we're going to call hydrogen a metal in this case, and you react them with oxygen, they can make oxides. But in this case, unlike above, there's no hydrogen gas because there was no hydrogen in that oxygen molecule to begin with. So metal plus oxygen makes a metal oxide. And then that last group, right, silver, is in the same group as platinum and gold. Right? Those are precious metals for a reason. Those metals are very unreactive. They don't tend to react anyway, anyhow. So they're not going to react with oxygen. They're not going to react with acids. They're not going to react with water. They basically just don't do anything. And so if you have silver or platinum or gold on a quiz or a test, and I'm asking you what products it's going to make when this reacts with that, you basically just say, well, it's not going to react. There's going to be no reaction, just like on that last slide. Right? Just like how magnesium could not replace calcium. If this was gold, it still wouldn't work, right? But gold doesn't react with anything. I'd have a no reaction no matter what the case was. So again, this is just generic. Right? I also want you to add a specific example for each one of these so you can see what it might look like. Right? So in that first group with lithium, we could just use lithium. Right? Lithium can react with water at any temperature, and it's going to make a hydroxide, so lithium hydroxide and hydrogen gas. Again, I would probably have to indicate the temperature if I need a certain temperature, but in this case, it really doesn't matter if it's hot, cold. It's going to work no matter what. I do have to balance this appropriately, so considering there's 3 hydrogens over here, I'm probably going to need to have 2 waters and then double this and double that to balance this overall. Otherwise, it could look different in that group because some of those are metals from group 2 that'll have a +2 charge. So barium will react with water, and it's going to look a little bit different because it'd be a barium hydroxide with 2 hydroxides in it already, plus hydrogen gas. In which case, the only thing I need to do to balance is make sure that there are 2 waters, because I need to have 2 oxygens on both sides. And that should give me 4 hydrogens and 1 barium on both sides. So it might look one way or the other, just make sure you can follow examples from your notes. But again, once you get to the second group, once you get to magnesium, you have to be careful. Because magnesium will also react with water, but it does so differently. First, I would have to know that the temperature was at least 100 degrees Celsius, right? I would have to know that that water was steam, right? That it was gaseous, right? I have to indicate a temperature some way, somehow for magnesium, or else I'm just going to write no reaction because it will not react with cold water. But since I do have 100 degrees Celsius, in this case, I am going to make a product, but it's going to be an oxide product, not a hydroxide. So I end up with magnesium and 1 oxide because they're both 2 charges. Otherwise, I did kick out those 2 hydrogens. And this one's nice because it's just balanced. I don't have to do anything to balance it. Right? So it's all 1 to 1 to 1 to 1. Otherwise, everything else in that second group is either likely to be a +2 charge or it's aluminum. And we already did aluminum in your notes for section 2, I believe. So you should know what an aluminum oxide looks like and how that would balance differently. Otherwise, again, cobalt's the next one. So again, in this case, I'm reacting with acids. So if I add a hydrochloric acid, anything containing hydrogen that's not water, you can assume is an acid in these cases. So cobalt in this hydrochloric acid, I don't need any special temperature. I just need to make sure cobalt's higher than hydrogen on the list, and it can displace it. Again, cobalt, we have two different charges for cobalt, if you remember. But when you are doing these types of reactions, when you're predicting products, I don't care what it is. If you don't know the charge, assume it's a 2, right? Because sometimes you'll know and sometimes you won't. Even if you did know, you'd be like, well, is it going to be a tin 2 or a tin 4? Right? When you're making these products, always assume it's the 2. Right? So unless it's aluminum or something from group 1, you're just automatically going to assume it has a +2 charge. And so I get this cobalt 2 chloride. And again, I'm displacing hydrogen, so I need to make hydrogen gas. Hydrogen is always diatomic. I can't just kick out the 1. I have to have 2, which makes this whole thing balance all overall anyway, because I had to have 2 hydrogen chlorides to get the 2 chlorines necessary for my cobalt chloride over here. So it's good that there's 2 and 2, because otherwise I wouldn't have the 2 and 2 over here to all balance out. Should be fine with this. So again, cobalt, nickel, tin, lead, all 4 of those, it's always going to be a 2, so they balance different. They balance the same as this one. And then finally we have our hydrogen group. Again, we're assuming hydrogen's a metal in this case, but all we're saying is that hydrogen can react with water, or with oxygen, to make, water. Right? That is actually a metal oxide, ironically. It can also be considered a non-metal oxide, because remember, we would call it a dihydrogen monoxide. We wouldn't call it a hydrogen oxide, because those are typically called nonmetals. But if you had copper with oxygen, you'd make a cuprous oxide, right? Or even possibly a cupric oxide. But you know that that can happen because the Statue of Liberty is green. So you know that copper can react with oxygen. So it depends on what it is. But again, if I had something like copper, I would always assume that it's going to make the 2 and not the other one. So in this case, I'm going to have a copper oxide like this, which is cupric oxide. And then I'd have to balance this overall, just like that. Now again, it could have been the cuprous oxide, but because I'm telling you as a rule to always assume it's the 2, if there's 2 options, go with the 2. But again, you should be familiar with that, because the Statue of Liberty is green, and it's green for a reason. And so it's made of copper, but it doesn't look like copper. It's not a brownish, reddish color. It's green. And that's because it's covered with copper oxides. Otherwise, that last group again, I'm kind of blurring my boundaries here. Remember, these are all separate from each other. That last group, if I had silver and I tried to react it with oxygen, I'd get nothing because silver is unreactive. It generally doesn't react. The only thing silver can do is displace platinum or gold because it's technically higher than those 2 things in some compound. Otherwise, silver is fairly unreactive and probably won't do any of the things that we're talking about. So just be ready to put a no reaction for any of those options. But there's a lot of times that you're going to have to say no reaction because you're going to have to pay attention to the details. Because again, it gets a little bit confusing here and there. But my basic rule of thumb when I'm looking at these things is understand that anything you can do, I can do better, right? If you're referring to, say, like a lithium, I meant to highlight that, a lithium compared to, say, like a cobalt, lithium's at the top of the list. It's at the top of the totem pole. It's the best, right? Anything that cobalt can do, lithium can do better, right? But cobalt can't do all the things that lithium can do. Cobalt, remember, cannot react with water. It doesn't matter if it's hot or cold water. It can't react with water to make oxides or hydroxides in hydrogen gas. Cobalt can only react with acids to make hydrogen gas. So it depends on the context, right? If I flip-flop lithium for cobalt, lithium can definitely react with, excuse me, I forgot to change the color again. Lithium, I still didn't change the color back. Lithium can react with hydrochloric acid, and you'd get a lithium chloride, and you'd get hydrogen gas. You'd have to balance it appropriately. Again, you'd probably go 2-2, and then I'd need another 2 over here. But if I tried to do the reverse, if I wanted to get cobalt to react with water, no matter how hot that water is, it's not going to work, right? Things above on our list, on our activity series, lithium can do any of these reactions that we've described. But silver can do none of those reactions that happened above it, right? So understand that I can mix and match. It doesn't have to be that specific group reacting with acids. I could have any metal reacting with an acid. Sometimes it'll work, sometimes it won't. Again, lithium can definitely react with an acid, but if I had silver and I tried to react it with an acid, I'd get nothing. Again, silver's below, right, on the list. It can't do it, right? Even copper is below hydrogen on my list. So even if it's in the same group as hydrogen, copper's in the same group as hydrogen, but it's below hydrogen, technically. So it can't displace hydrogen. It can't replace hydrogen in an acid. And hydrogen obviously can't displace itself. That should be pretty obvious. So you're going to have a lot of cases when you're going to do no reactions, but remember, anything you can do, I can do better. If it's actually above that reaction on our activity series, it can definitely do it. And then finally, you also have halogen displacements to worry about, right? So a couple examples there just to remember. These are a little bit different. I've been screwing these up already on our homework so far, right? Bromine doesn't replace potassium. It replaces iodine because it's more like iodine. Right? They're both halogens. So if you have a single displacement with a halogen, it should replace the other halogen. The metal stays. So I'm trying to kick out the iodine, bring in a bromine. It ends up looking a little bit like this, but this actually will occur. This reaction will work. But if I flipped it, or if I changed it, just because bromine can replace iodine doesn't mean it can replace anything. And bromine is actually less active than fluorine and cannot replace it. Now, halogens are not on our activity series, but you can write down a quick halogen activity series if you want, because there's only 4 of them. And you don't really need to write it down because it's already on your periodic table. Fluorine's at the top, iodine's at the bottom. That means iodine is the least reactive of these 4 elements. So bromine can replace iodine because bromine is higher than iodine on the list, whereas bromine cannot replace fluorine because it's lower on the list. So in this second example here, I'd actually get a no reaction. Remember, you're trying to learn how to use these activity series. You got to predict whether you will get those products or you won't. Sometimes you will, sometimes you won't. You got to know what you're doing. You got to follow, model off of examples in your notes. But sometimes you don't make those products. You have to recognize that, oh, that metal's not active enough to do this. So that's actually going to be a no reaction. And these are halogens, but same thing. Any single displacement reaction, you always have to refer to an activity series. You always have to know what will replace what. All right, so that's enough for the start of the notes. There is a second video that will go through all these examples, but I want you to go through those examples and actually try to do those for yourself first. And I'll also say that in the other video because it's an old video. So make sure you try to come up with products for all those other examples in your notes, on the back of your notes. But then watch that video and see if you did it right, and we should be good. Right?